What is a logistic model? What would it be used for? So a logistic function is a sigmoidal function. They're synonyms. You need to know both names. They're used to model growth to equilibrium. So what do I mean by equilibrium? So we could have a stable state such as your pH, which is the concentration of hydrogen ions. And if the balance is wrong, then there's going to be some sort of reaction that goes on to bring that concentration back to whatever the pH should be of the substance. You could have a stable state being the temperature. So something like you have some food in your freezer. This is looking more like a microwave than a freezer, but you have food in the freezer, and then you take that food. That food it has an equilibrium. It's reached an equilibrium with its environment. It's cold, and then you take it out of the freezer. Now it's in a new environment, so it has to get into equilibrium with room temperature. So it will start thawing. That thawing process is frequently modeled by a logistic function. And a third thing would be something like a population with predator-prey or resource management. Population with restricted resources. So let's say that there's only, I don't know, 100, the current field in some location can only feed 100 ducks. And I don't know why ducks are eating in a field, but let's say that it can only support 100 ducks. And then all of a sudden more plants are growing. So for that new change, the new influx of food for the ducks now means that they have to go from their old equilibrium of 100 ducks to whatever the new equilibrium of maybe now that it can support 120 ducks. So that's one equilibrium going to a new equilibrium. How does it get there? Is a logistic function, and it looks like this. You have, say, population size over time. It has an asymptote here and an asymptote up here. And in the middle, it looks exponential here, a little linear here, and then exponential again up here before it levels off to be an asymptote. I believe sigmoid came from it looking literally like an S. So this is your basic sigmoidal curve. It has an asymptote at y equals 0. It has an asymptote at y equals 1. So there are two horizontal asymptotes. And then it passes through a point halfway between those asymptotes. In this case, it's 0, 1/2. This is what the graph looks like. So A is our amplitude. And that represents essentially your second asymptote. So your first asymptote is at y equals 0. Your second asymptote is at y equals a. Then B and C change the curvature. So it changes the slope here and how quickly it levels off. You don't have to worry about exactly how B and C affect this, but let's look at the important things that I would ask you about. So the domain is going to be all real numbers, unless it's restricted by the word problem. The range is going to be from one of your asymptotes, so that's going to be from 0 up to A. Now, unlike in Gaussians, here the maximum value is not actually hit because it's an asymptote. So that's why this one is y is less than a, whereas the other one was less than or equal to a. Your asymptotes are at y equals 0, and y equals a, and then your inflection point. So this is the point in the middle. That inflection point is based off of is based off of halfway between the asymptotes. So the y coordinate would be a over 2. And then how would you find the x coordinate? Well, you could plug a over 2 in for y, and then you can find that. So in other words, you could take the inverse and plug in a over 2, and that will give out your inflection point. The main thing that you need to know is that you're starting from one equilibrium of a population, so some stable state. Something changes that allows the population to change, and then it takes a sigmoidal path to the new stable state of the system. That is a logistic model.